Hi everyone, Mrs. And today we are going to be doing some gas stoichiometry. Now we've done stoichiometry before, but now we have some extra skills where we can calculate the moles of gases. So let's put that into our stoichiometry process. Stoichiometry is nothing new for us, but up until now we've not done stoichiometry with gases. So let's just remind ourselves what the process is for completing stoichiometry. First of all, you need to have your balanced equation. Very important because, of course, your mole ratio depends on your ability to balance that equation correctly. The next step is to calculate the moles of the known. So your question is always going to give you enough information to calculate the moles of something. And that is what we're going to call our known value. After that, we're going to use the mole ratio, and that will allow us, if we know the moles of the known, to calculate the moles of the unknown. The unknown is normally what the question is asking us to find. And then finally, the last step of the question will be converting to the required quantity. So where do gases come into this? We have learned how to calculate the number of moles of gases, and we can do this at STP or SLC using moles is equal to the volume divided by the molar volume, and we know that our molar volume at STP is 22.4 litres per mole and our molar volume at SLC is 24.5 litres per mole. We also know, if we're not at STP or SLC, that we have our ideal gas equation, PV equals nRT, and rearranging that to find moles, it's PV over RT. So we do have some tools at our disposal now to be able to calculate moles when we're dealing with gases. Now sometimes your known will be a gas, and then you will use those formulae to calculate the number of moles. Sometimes your unknown will be the gas, and this is where you're going to use the formulae to convert between moles and other quantities of gas. So you never know, you may be asked to find out what the pressure is, and you may be asked to find out what the temperature is. So you just don't know what the question's going to ask you, but as long as you know moles and a few other things, you always have these formulae that can help you determine other quantities. So let's have a look. We've got 3 examples for you today. I've got an easy example, and I've got a slightly harder example, and then I've got a really mean example for you. All right, let's get cracking. So our first example, the synthesis of sodium chloride occurs according to the reaction sodium plus chlorine gives sodium chloride. What volume of chlorine at STP is necessary for complete reaction of 4.81 grams of sodium metal? All right, let's get the stoichiometry process on. So first of all, what do we want? We want a balanced equation. Is that equation balanced? Well, I can see that I have 1 sodium and 2 chlorines here, and I have 1 sodium and 1 chlorine there. So no, that's not balanced. So I'm going to need to balance the equation. And I'm going to do that by saying I've got 2 chlorines on the left, but only 1 on the right. So I'm going to double the NaCl, the compound containing chlorine, over on the right. Now my chlorines are balanced. Unfortunately, in that step, I've unbalanced my sodiums. Now I have 2 sodiums over here on the right, but only 1 on the left. So I'm going to need to double that as well. Now my equation is balanced, and I can move on to step 2. I'm going to find the moles of the known. Now, what do we know? We know we're given that the mass of sodium is 4.81 grams. And we know that we can, if we have mass of a substance, we can use mass over molar mass to convert to moles. So in this case, my mass is 4.81 grams. Molar mass, or the relative atomic mass of sodium, is 22.99 grams per mole. And so I can find out that I have 0.209 moles. Remember, 4.81 is 3 significant figures, so I can only give my answer to 3 significant figures. Now I know my moles of the known. It's time to use the mole ratio. So when we use the mole ratio, we always put our unknown over our known, because we want our unknown to be in the numerator to make the algebra easier. So our unknown is the chlorine gas. Our known is the sodium. And our mole ratio, which is taken from the coefficients in the equation, is for chlorine. Here we have a coefficient that's 1, and for sodium 2. So this is 1 over 2. And if we do a bit of algebra now, multiplying both sides by moles of sodium, we have moles of chlorine is half the moles of sodium. And if we compute that, we get 0.105, rounding off to 3 significant figures again. So now we've got the moles of our unknown. It's time for step 4, converting to the required quantity. And in this step, the required quantity is the volume. So we need to find the volume of chlorine gas. And we know we're at STP, so we know that the molar volume of any gas at STP is 22.41 litres per mole. Now it's a simple case of volume equals moles times by molar volume, which is 0.105 multiplied by 22.41. And we come out with 2.34 litres. Again, 3 significant figures, because that is what our measurement in the question has. So that's a fairly simple one. Anytime you're at STP or SLC, your calculation of volume is going to be quite an easy thing to do. Let's look at a slightly harder example. If water is added to magnesium nitride, ammonia gas is produced when the mixture is heated. When excess water is added to 10.3 grams of magnesium nitride, what volume of ammonia gas would be collected at 24 degrees Celsius and 752 millimeters of mercury? Just follow the process. So again, we have been given a mass, but first of all, always balanced equation. Remember, in your equation balancing, leave oxygen and hydrogen until last. Start with the other stuff. So I'm going to start with my magnesiums. I can see here I have 3 of them, but over here only 1. So I'm going to multiply that compound that contains the magnesium by 3, and now my magnesiums balance. Next step, nitrogens. I have 2 here, but only 1 here. So I'm going to need to double that. Now it's time to look at the waters. I have 1 here. I've got 2 hydrogens and 1 oxygen. Here I've got 3 oxygens and I've got 6 hydrogens. So I can see here that what I'm going to need to do is multiply my water by 3. That's going to end up with 6 hydrogens and 3 oxygens, and now we are balanced. Now, step 2. Our known substance we're given a lot of information in this question, but we're asked what volume of ammonia gas. So this is going to be our unknown. And we're told stuff about magnesium nitride. So that's our known. So our moles of our known is mass 10.3 over molar mass. Now there's a calculation here for molar mass because it's not just one atom. So you've got 3 magnesiums and 2 nitrogens. Run that through your calculator and you will find that that is 0.102 moles. Again, 3 significant figures because the 10.3 was 3 significant figures. Time to use the mole ratio. Putting your unknown, we want to know about ammonia, so that is our unknown on the top. Our known, magnesium nitride. And from the balanced equation, our ammonia has a coefficient of 2. Our magnesium nitride has a coefficient of 1. So that means we're going to need to multiply by 2. So our moles of ammonia, this is just a simple, just taking this and multiplying on the other side. So 2 times by 0.102 is 0.204 moles. Now we've got the moles, we need to convert to the required quantity, and the required quantity is volume. So because we're given a temperature and a pressure, and we've calculated a number of moles, we can use the ideal gas law, PV equals nRT. So volume is equal to nRT over P. But we have a little bit of work to do because we are given our pressure and our temperature in units that are going to need converting. So let's convert our pressure. We've got 752 millimeters of mercury, and we want that in kilopascals. So using our multiply by 1 method, cancelling the millimeters of mercury, and we end up with 100 kilopascals. 3 significant figures because this is 3 significant figures. Now, temperature. Temperature is in degrees Celsius, and that is never going to do. So 24 degrees Celsius is equal to 24 plus 273 for Kelvin. That's 297 Kelvin. Now we can plug it. Now we've got our temperature and our pressure in the correct units. We can plug into our equation. So moles is 0.204, R 8.31. Temperature was, oh, that should be Kelvin over here, not litres. I'm sure you picked up that temperatures should not be in litres. 297 Kelvin over our pressure, which was 100 kilopascals. And we get 5.02 litres. Okay, a little bit more involved, but still well within your circle of competence. You know how to do the ideal gas law problems. We've learned about that. You know how to do stoichiometry. It's just a matter of drawing those skills into the same question. Let's get nasty. All right. Ammonia and hydrogen chloride combine to form ammonium chloride according to this equation. 4.21 litres of ammonia at 27 degrees and 1.02 atmosphere is combined with 5.3 litres of hydrogen chloride, at 26 degrees and 0.998 atmosphere. What mass of ammonium chloride will be produced? Which gas is the limiting reactant? Oh, here's a clue in the question. This is a limiting reactant problem. So we're going to still go through the stoichiometry process, but we're going to be held up by looking for which is the limiting reactant. But that's okay. We've done limiting reactant problems. I'm confident we can get through this. So first step in the stoichiometry process is the balanced equation. And thank goodness this one is balanced. I like that it's balanced because there is nothing better in a limiting reactant problem than a 1-to-1 mole ratio. It makes life a lot simpler. Calculating the moles of the known, we don't know which one is the known. Our known has to be the limiting reactant. We only do stoichiometry using the limiting reactant. So we're going to have to explore which one of those it is. So we've got two substances. We've got ammonia and we have HCl, hydrogen chloride gas. It's not hydrochloric acid until you dissolve it in water. So we're going to find the moles of both of them and see which one is the limiting reactant. Now, what do we know? For ammonia, we know that the volume is 4.21 litres. We know that the temperature is 27 degrees Celsius. Of course, you're not going to use that in a gas laws problem. You're going to convert that to Kelvin. We know that the pressure is 1.02 atmospheres. Now, either we're going to convert that to kilopascals and use 8.31 for the universal gas constant, or we're going to use 0.08026? I would look it up. I will be converting this to kilopascals. So if I convert that to kilopascals, it's 101 kilopascals. And if I'm using kilopascals and Kelvin and litres, then my gas constant is 8.31. So PV equals nRT. So moles is equal to PV over RT. We have 101. Oh, sorry. Oh, I got my kilopascals wrong. That's actually 103 kilopascals. Okay, now we're set. I'm sorry if you were going, hang on, I get 103. You were right. So let's sub in. So pressure is 103 kilopascals. And our volume is 4.21. Our R is 8.31. And our temperature is 300. Bringing our moles to 0.175. So now we know how many moles of the ammonia we've got, but how many moles of the HCl do we have? Same calculation. Volume this time is 5.35. Temperature this time is 26 degrees Celsius. And of course, we're going to convert that to 299 Kelvin. Our pressure is 0.998 atmosphere. We're going to convert that to kilopascals. And that's where my 101 comes from. R is 8.31. and moles is PV over RT. Pressure 101 times by volume 5.35 over R 8.31 times by temperature 299. Number of moles calculated is 0.218 moles. Now that we have both the moles, we can compare them. If we look at our equation, what we see is for the ammonia, we've got 0.175 moles. And for the HCl, we've got 0.218 moles. But our equation says they react 1 to 1. And that means this one's going to run out. The ammonia will run out. And that makes it the limiting reactant. In the end, you'll have some of this will be left over. And that is your excess reactant. You're actually asked which is the limiting and which is the excess reactant. So you have your answer there and there. However, you need to go on and perform your stoichiometry. Stoichiometry only uses the limiting reactant. So we are now going to totally ignore the HCl. No stoichiometry for your HCl. Excess reactants do not get used in stoichiometry. So our unknown, what we're trying to calculate, we've almost forgotten. We've had to do so much work on the way, we've almost forgotten what we're calculating. We're going to use our limiting reactant, and it's a 1-to-1 mole ratio there. So the moles of ammonium chloride will be equal to the moles of ammonia, which is 0.175 moles. But that's not the end of it. We still have to convert to the required quantity. I know you're thinking, do you have enough time in an exam to complete one of these questions? If you practice a lot, you'll get fast at them. Mass is equal to moles times by molar mass. Moles is 0.175. Your molar mass is going to be 14.01 for nitrogen, plus 4 into 1.01 for hydrogen, plus 35.45 for chlorine. And that comes to 9.34 grams. All done, all solved. They couldn't really come too much nastier than that question. I can think of one way to make it nastier. I could actually involve Dalton's law as well, and I could have those two gases separated into two flasks, and I could open a valve between them and force you to work out the pressure, their partial pressures. But I'm not going to do that today. Anyhow, good luck with your gas stoichiometry. I will see you in the next video.